Hi to everyone and welcome to this AMETEK Land webinar. Okay, right now I'd like to introduce today's presenter, Derek Stuart. Derek is the Global Product Manager of Power, Combustion, and Environment at AMETEK Land. He has more than 25 years' experience in industrial gas and dust concentration measurements. As a product development specialist, he was responsible for the design of several continuous emissions monitors, including the successful 4500 Opacity monitor, which is used to monitor particulate matter emissions in stacked gases worldwide. Derek is a chartered physicist, a member of ASTM with contributions to several ASTM standards, and holds 2 patents in the field of opacity monitoring. So Derek, welcome to today's event. It's our pleasure to have you here. And with that, I'm going to pass things along to you to get us started. So Derek, go right ahead.
Hello, I'm Derek Stewart, Global Product Manager for Power at AMETEK Land, and the title of my talk today is Pollution Control and Safety Monitoring in Power Plants. So I'm going to talk about technologies which are available to improve the efficient, clean, and safe operation of thermal power plants. Regardless of the fuel used, an accurate knowledge of process conditions is essential to ensure a thermal power plant can be operated with maximum safety, minimum cost, and minimum adverse effect on the environment. I'll show you today how AMETEK Land has products which can help you to achieve these aims. AMETEK Land was founded in 1947 by Tom Land as Land Pyrometers. In its 72-year history, it's been responsible for many innovations in thermal and combustion measurement technology. It's now a world-leading manufacturer of instrumentation for industrial infrared non-contact temperature measurement, combustion efficiency, and environmental pollution emissions. The company remained in the control of the Land family for over 50 years, but has been part of the $5 billion AMETEK Incorporated since 2006. The AMETEK Land product range includes a variety of industrial measurement devices which are used to measure key process parameters, usually in harsh environments. These include single-point pyrometers, temperature scanners, and thermal imagers, as well as monitors for combustion efficiency, environmental emissions, and site safety. Today, I'll be concentrating on the last 2 items in this list, our opacity and dust monitors and our carbon monoxide monitors. There are many areas of a power plant where accurate measurements are important. Today, I'm going to focus on 2 areas in particular: fuel handling and emissions measurements. For fuel handling, the emphasis will be on detecting spontaneous heating and spontaneous combustion for safety purposes, and in emissions measurement, I'll be looking at different approaches to measuring particulate matter such as fly ash leaving the stack or duct. When coal is transported from the mine to the plant, it passes through a lot of different steps. Typically, it's loaded onto a train, unloaded onto a storage pile, coarsely crushed, moved to a day silo, and finally pulverized before being transported to the boiler. At each stage, it's important to ensure the coal is in good condition and can be moved safely to the next. Biomass pellets are increasingly being used in European and East Asian power plants because they reduce CO2 emissions when compared to burning coal, and they have a similar journey between the pellet mill and the power plant. In fact, the largest pellet producers are in North America, so the pellets usually have to make an ocean journey before they reach their destination. I'm going to discuss the areas of risk in fuel handling systems and the technologies available to detect spontaneous heating and spontaneous combustion. Our aim is always to identify the precursors so that the site operation can make the fuel safe before a fire occurs. Of critical importance is the problem of oxidation. When coal or biomass particles are exposed to air, the volatile components combine with oxygen in an exothermic reaction, leading to spontaneous heating. Since this part of my presentation concerns fire and explosions, let's review some basic theory. The fire triangle identifies the 3 components that are needed for a fire to occur: fuel, oxygen from the air, and an ignition source. Take away any one of these components and we no longer have a fire. An explosion requires two additional elements and is usually illustrated as a pentagon. These are the dispersion of the fuel with the oxygen, which allows very rapid combustion, and also confinement, which allows a pressure wave to build up and then release suddenly. The first stage, when a carbon-containing fuel begins to burn, is the production of carbon monoxide and heat. If sufficient oxygen is available, complete combustion occurs with the conversion of the CO to CO2 and a lot more heat. When spontaneous heating is occurring, the combustion is inefficient and only proceeds to the first stage. Therefore, the telltale signs of spontaneous heating and spontaneous combustion are the emission of carbon monoxide and a rise in the temperature of the fuel. Once a problem has been detected, the site operator can take steps to neutralize it, generally by using an inert gas to displace the oxygen or by removing the fuel from the storage area. As coal ages, it tends to oxidize and to crumble. This increases the surface area, and so the rate of oxidation increases. Oxidation is an exothermic reaction, heating the fuel and further increasing the oxidation rate, so that a runaway condition can develop, eventually causing spontaneous combustion when the coal catches fire. As well as the obvious safety concerns, spontaneous heating and combustion can result in the loss of the purchased coal, which is no longer available for use in the boiler. Lower rank coals are more susceptible to oxidation than hard coals, and subbituminous coals can lose as much as 1.5% of their mass between the mine and the power plant. The best known subbituminous coals are those from the Powder River Basin in the western United States. Biomass also suffers from spontaneous heating. In addition to oxidation, biological action from bacteria and fungi can cause heating in the stored biomass. Depending on the base wood, it can produce enough carbon monoxide to constitute a toxic gas hazard within an enclosed space. The image here shows a pile of stored wood chips which had become wet and where microbial action generated enough heat that the fuel caught fire when it was exposed to the air. Several technologies are available to detect spontaneous combustion and give early warning before it develops into a fire. Today, I shall concentrate on the instruments manufactured by AMETEK Land, but of course we are not the only supplier with this type of equipment. Thermal imaging is ideal for measurements on open or semi-enclosed storage areas such as coal piles and biomass storage domes. Infrared scanners can detect small amounts of overheating material on a conveyor belt, and carbon monoxide monitors can detect the CO emitted as fuel oxidizes within an enclosed space such as a silo or a pulverizer. This illustration shows schematically what happens as spontaneous heating begins and progresses. Large amounts of CO are produced by the inefficient oxidation associated with spontaneous combustion. Now, ambient air contains very low concentrations of CO, usually well below 10 ppm, so a significantly higher concentration provides a fast and highly specific indication that unwanted oxidation is occurring. As time goes on, there will be enough heat buildup to give an observable temperature rise, and this is also a clear indication that something bad is happening to the fuel. We have three ways to detect spontaneous heating. Our aim is to detect the danger signs before a fire is present. Carbon monoxide emissions give the earliest indication of a problem, but they can only be used in enclosed spaces. This is because wind will quickly disperse any emissions before a measurable concentration can accumulate in an open area such as a storage pile. That makes CO detection ideal for use in silos, storage domes, and pulverizers. Temperature sensors are another option for monitoring and preventing spontaneous combustion. They give a direct indication that heating is occurring. Because of the time taken for a measurable temperature change to build up, a temperature sensor gives a slower indication of a problem compared to a CO monitor. However, it can be used in an open area such as a coal pile or a conveyor belt which is exposed to air movements. Finally, there's a fire detection system. By the time this triggers, we have a serious problem and are definitely beyond the stage of taking preventative action. Let's start by looking at the options for detecting spontaneous heating within an outdoor storage pile. The size of the pile, and the dangers posed by voids within the pile make it difficult and potentially dangerous to use manual methods for monitoring these situations. Infrared thermometry is a non-contact technique that allows for remote temperature measurement. A thermal imager can give a two-dimensional map of the coal pile's surface temperature. It's important to note that the non-contact temperature measurements can only determine the surface temperature of the fuel, so they may miss a buried hotspot. However, the heat generated by the oxidizing fuel will eventually warm the surrounding material, and the hot gases given off will transfer heat to the surface through convection. A study by Spiero and colleagues a few years ago noted that infrared thermography is very efficient at detecting hotspots in coal piles, and the losses calculated using the technique correlate well with those measured directly using thermocouple probes. The illustration shows a fixed thermal imager with a long focal length lens attached to a pan and tilt mount. This arrangement allows it to repeatedly scan across the storage pile to give a high-resolution image without sacrificing coverage. Depending on the size and geometry of the storage area, several separate thermal imagers may be needed. The system illustrated here has 4 imagers with 2 remote consoles displaying the images and processing and storing the data. This image shows a coal pile with a vehicle in the foreground. This is a potential false alarm as the exhaust appears as a hotspot. We can avoid problems by applying a time delay so the alarm is only flagged if the hotspot has been present for a sufficiently long time period. Here is the display screen from a 3-imager system. In the left-hand panel, we see the live thermal image from each camera, with the color scheme chosen to give emphasis to the temperature range of interest. In the upper panel is an image showing an area of high temperature, highlighted. The bottom panel shows the patrol record for each of the imagers, with the status of the designated zones. The upper camera has a total of 12 zones of interest, the middle has 4, and the lower has 8. For each zone, green indicates no problem detected, pink shows that 1 pass found a problem, and red is an alarm condition triggered by 3 consecutive passes, each with a temperature above threshold. Conveyor belts are used at many points within a power plant. They're also used in pellet production and shipping facilities. If we can detect a small amount of smouldering material on a belt, it can be diverted or extinguished before it's loaded into a silo or onto a ship, where it can ignite a much larger amount of fuel and cause serious damage. We have a quite specific set of issues in detecting spontaneous combustion in material on a moving conveyor, not least that it's moving rather fast. In addition to the danger that it poses to plant and personnel downstream, hot material can damage the conveyor itself and cause expensive downtime. If a conveyor can't transport fuel to the boiler, the plant can't generate electricity. Here we see an AMETEK Land HotSpotIR infrared line scanner mounted above a coal conveyor. This is a variation on a thermal imager and is specifically designed to map the temperature of a moving object such as a belt. The scanner has an 80-degree field of view, so the height above the belt should be a little more than the belt width divided by 1.6. Line scanning uses a single infrared detector and a rotating mirror that repeatedly scans across the moving object perpendicular to its direction of travel. The combination of a scanning mirror and the linear movement of the conveyor allows the signal processor to build up a two-dimensional map of temperature. A typical instrument can resolve 1,000 points per scan, with as many as 100 scans per second, giving very high spatial and temporal resolution. Line scanning has significant advantages over conventional thermal imaging. It has only a single infrared sensor, so the consistency of temperature measurement is better than an image sensor, which may have over 100,000 separate pixels, each with a slightly different responsivity. It's important to remember that a line scanner, like any other thermal imager, cannot see through the fuel and is limited to measuring surface temperature. Line scanners have also found applications to detect hot spots in rail cars, either by measuring the temperature of the car itself or by looking at the stream of coal as it's being unloaded from the bottom of the car. The high resolution of a line scanner gives it significant advantages over alternative methods such as spot pyrometers and spark detectors. These work by measuring the radiation given off over a much larger area. The example here shows a 15mm hotspot with a temperature 100 degrees Celsius above that of the rest of the material. This fills only 0.02% of the field of view of the pyrometer and will register only 0.2 degrees Celsius difference on that pyrometer. A spark detector is somewhat more sensitive, but still will not register such a small hot object. A line scanner can resolve 1,000 spots across the width of the conveyor and will easily detect the same 15mm diameter hotspot and flag an alarm. A typical line scanner generates 100,000 data points every second. It's important to present this in a suitable form so we don't overwhelm the plant operator with information that cannot be used. A simple processing scheme indicates the peak temperature from each scan as a 4 to 20 milliamp signal, along with a relay which indicates that the peak is above an alarm temperature. The new AMETEK Land LMG Mark II processor allows up to 4 separate scanners to be connected to a single display. We can also choose to use a full graphical display with image processing facilities similar to those of a thermal imager. A peak-picking processor can detect a hotspot. Using all of the data allows the operator to see exactly what's going on and especially allows him or her to establish zones of interest within the image. In this example, we are measuring both the temperature of the material on the belt in the central area and the temperature of the edge of the belt. This allows us to detect an overheating edge, which usually occurs when a bearing is not running correctly and is causing a lot of friction. At least one biomass fire is thought to have been caused by an overheating bearing. It's important to choose the correct installation location for the scanner. The most obvious is directly above the conveyor, looking down, but mounting at a transfer point allows it to see further into the material as it fans out, and the increased exposure to air can also cause the temperature of any hotspots to increase. So summing up, a hotspot detector is a rapidly responding sensor which can identify hot, smouldering material on a moving conveyor with very high spatial resolution. A simple signal processor can reduce a lot of data to a single number, or it can be connected to a full-featured image processor for more in-depth analysis. Silos are used for short-term storage of fuel close to the boiler. They give protection from the weather and keep the fuel dry. Wet coal reduces combustion efficiency, but enclosed storage is essential for biomass pellets because they will simply disintegrate if they become wet. Because they're enclosed spaces, silos and storage domes are best monitored using a carbon monoxide sensor. The sample point should be located near the top of the silo so it can measure the gas in the headspace above the fuel. In most cases, a single sample point is sufficient because natural convection ensures the gases in the headspace are well mixed. Very large or highly asymmetric storage volumes may require additional sample points to ensure adequate coverage. Some silos employ a nitrogen blanket to reduce the risk of spontaneous combustion, so an oxygen concentration measurement is used to confirm that the gas injection rate is sufficient. The power of CO monitoring comes from the fact that CO concentration in ambient air is very low, even in an industrial environment, so the presence of CO gas is a clear indication that something is going wrong. Choosing an appropriate alarm level for the CO sensor is also important. A low alarm threshold gives the earliest warning of a problem, but it can result in nuisance alarms. An excessively high threshold will allow spontaneous heating to progress to the point of being hazardous without giving an alarm. The exact value is specific to the fuel type and to the storage location, but in many cases a value between 100 and 200 ppm works well. An alternative to a level alarm is a rate of change alarm. This type of alarm ignores the background level of CO, but responds to the rapid increase that's associated with early stages of spontaneous combustion. I'd just like to emphasize the point at the bottom of the slide. CO monitoring only works in enclosed spaces. Open areas such as storage piles and conveyors have too much air movement, so any CO is carried away as soon as it forms. The Land Silowatch monitor is specifically designed to measure CO in a silo headspace. It's a self-contained unit combining CO sensors with sample conditioning, signal processing, and calibration verification in a single cabinet. It's engineered to be robust and to function reliably in a plant environment. As well as its alarm functions, it gives a 4 to 20 mA analog output, so you can follow trends in the silo CO concentration. It's important to verify correct operation of the sensor, otherwise a negative indication can give a false sense of security. For example, a sensor can be plugged with coal dust so that it no longer is exposed to the silo atmosphere, or the sensor can fail to zero output. That means a faulty instrument will indicate a CO concentration of 0, giving a false sense of security. The silo sample probe is a simple stainless steel tube with a sintered filter to prevent dust particles from entering the sample system and causing a blockage. Periodic blowback with compressed air keeps the filter clean for minimal maintenance. Any CO formed by spontaneous combustion will be detected in the headspace of the silo, so the sample point must be above the highest fill level, and it's important that the sample probe does not interfere with the loading chute. In most cases, convection ensures the gases in the headspace are well mixed. Depending on the local environmental conditions, a freeze-protected sample line may be needed between the sample point and the analyzer to prevent moisture from the fuel from freezing and causing a blockage. 2 sample tubes are generally used, one for the gas sample and one for the calibration gas returning to the probe. Running the cal gas up to the probe allows us to correct for any losses and also ensures that a leaking or blocked sample system will not go undetected. The inside of a silo is generally considered to be a hazardous area, but this does not cause us any problems because the only thing inside the silo is the stainless steel sample probe, and it is classed as a simple device. In cases where the analyzer has to be mounted in the hazardous area, a Z-purge allows it to meet Class 2 Div 2 specifications. A dual stream analyzer allows simultaneous and continuous measurements from 2 adjacent silos. In addition to the savings on the cost of the instrument, reducing the number of cabinets saves significantly on the installation costs and on the amount of space needed for the installation. The final area of concern in fuel handling is the mill or pulverizer, where the fuel is crushed to a fine powder before being fed to the burner. Mills are large and powerful devices, so a fire or explosion within the mill can cause significant damage and lost production. The greatest risk of fire or explosion comes during startup and shutdown, as this is when there is an explosive mixture of fuel and air within the mill. The risk is lower when it's in operation, as the coal dust concentration is generally above the upper explosive limit. Restarting a hot mill is especially hazardous as it's full of finely divided fuel, and it's likely that this is already oxidizing to some extent. One of the most interesting reasons for using a CO monitor is that it allows the mill to be operated at a higher temperature without losing a margin of safety. Increasing the temperature of the combustion air feed improves efficiency and so reduces the amount of fuel used to operate the boiler. That means a CO monitor on the mill improves safety, saves money, and reduces emissions of greenhouse gases. The best place to sample the gases within the mill is at the classifier outlet. There's 2 reasons for this. Firstly, the fuel particles are all moving in the same direction, so an insertion probe can be shielded to prevent abrasion. And secondly, the gases have been thoroughly mixed by the movement of the pulverizer, so we can be confident we're measuring a representative sample of what's going on inside it. The AMETEK Land mill probe is specially designed to withstand the aggressive environment at the mill outlet. It has a large area stainless steel filter to resist blockage, a blowback facility for self-cleaning, and a hardened steel abrasion shield to protect the filter from impact from the high concentration of high-velocity coal dust passing through the mill outlet. An alternative sampling device is available for applications where it's undesirable to have a probe penetrating into the sample stream. For example, where the sample has to be drawn directly from the mill body rather than the classifier outlet. This device consists of a sintered ceramic filter mounted in a stainless steel body. By placing the sample device outside the stream of pulverized fuel, we can isolate it and remove the filter for cleaning even when the mill is in operation. So far, we've discussed the concepts behind the detection of spontaneous heating and spontaneous combustion for plant detection. Now let's look at some concrete examples where operators are using these analyzers to enhance the safety of their operations. The first example is a site which had 3 mill explosions in the space of 5 years and decided to install AMETEK Land Millwatch CO monitors. They burn subbituminous Powder River Basin coal, which is well known for its propensity for self-heating. After installing the Millwatch analyzers, they ran for 3 years with no explosions, and so far as I'm aware, they're still running safely and successfully. Here's a graph showing how a hazardous condition was identified and made safe without shutting down the boiler. The image shows the CO concentration and mill temperature. Initially, the mill was running normally with CO below 10 ppm and stable temperature. Around 8 pm, the operators saw a sudden increase in the CO concentration, but there was no change in the mill temperature. They decided to shut down the mill, which caused the CO to come back down and the temperature to drop towards ambient. The boiler output was reduced as the mill came offline, but they were still able to generate 300 megawatts using the remaining mills. The mill came back into service just before the 11 pm, and you can see a small spike in CO as the fuel was introduced to the mill. In conclusion, they had a potential fire or explosion which was avoided, and the only consequence was to reduce output for 4 hours. Drax Power Plant in the UK was at one time Europe's largest coal-fired power plant, with 6 650 megawatt generating units. Over the past 6 years, they have converted 3 units to run entirely on biomass, with a 4th conversion recently completed. The pellet fuel is stored in 4 huge domes, each measuring 50 meters high. They use both land CO monitors and our HotSpotIR line scanners to monitor the condition of the fuel within the plant, and this has helped them to maintain their excellent safety record. Sunflower Electric in Kansas have 5 mills fed from 5 silos. They are using twin-stream Millwatch and twin-stream Silowatch to monitor their fuel conditions, and these have been running successfully since 2016. Now we're going to move to the other end of the process and look at some of the technologies that are available to measure emissions of dust and fine particles from the stack. Land specializes in dust and opacity measurements, so the next few slides will examine these technologies in some detail. Stack gas emissions are regulated throughout the world to protect human health and to minimize damage to the wider environment. To ensure compliance with the various regulations, plant operators have to measure the emissions and report them to the relevant authority. This may be the Environmental Protection Agency, the State Department of Environmental Protection, or another regulatory body. There are several ways for us to detect the low levels of dust that are emitted from a modern power plant. Most of these depend on the interaction between light and the particles in the flue gas. There are several types of interaction, and the strength of each depends on the concentration of the particles. Traditionally, we've measured the amount of light transmitted using an opacity monitor. More recently, instruments have employed some form of light scattering. Forward, side, and back scattering are all used. In this illustration, the back scattering is shown as reflection, which is essentially the same thing. No matter which sensing technique is used, the sensor does not measure the dust concentration directly, but measures a parameter related to that concentration. AMETEK Land offers 2 different sensing technologies for measuring particles in flue gases. The 4500 Mark III is a traditional opacity monitor measuring the amount of light transmitted across the stack. It can be used in most power generation applications in North America, especially those where the emission limits are set in percentage opacity. The 4650 PM probe uses laser light scattering to measure low-level dust concentrations in the cleanest processes. It can also be used in power generation applications subject to the US EPA's Mercury and Air Toxics, or MATS rule. Because particulate matter and opacity measurements are essentially 2 ways of looking at the same thing, it's important to understand the differences. A PM monitor measures in units of milligrams per cubic meter, whereas an opacity monitor measures percent opacity. A PM monitor can use a variety of different measuring techniques, including some which are not based on optical properties of the particles. An opacity monitor is, by definition, measuring transmission, so it has to use a transmissometer. A PM monitor requires a correlation test, so it can relate the measured parameter, light scattering or whatever, to the dust concentration. An opacity monitor leaves the factory fully calibrated and does not need further calibration, though it is generally necessary to verify the linearity of an opacity monitor using traceable, neutral density optical filters. Finally, PM measurements are used throughout Europe, most of Asia, and parts of Latin America. Opacity is most widely used in the US, but is also used in some countries in South America and in Asia. As I mentioned in the previous slide, a PM monitor uses an inferential measurement, and so it requires a correlation test to relate the measured parameter, such as light scattering, to the dust concentration. The drawback of the correlation test is that it's rather time-consuming and expensive, since it generally requires several days of work by a skilled stack test team. The AMETEK Land 4500 Mark III is an opacity monitor which meets the requirements of European and North American compliance rules. It has Qual 1 approval in Europe, and each instrument comes with a certificate of conformity showing compliance to ASTM D6216 as required by the US EPA Performance Specification 1. It's designed for the highest reliability in the harsh conditions associated with stack-mounted instruments. It has NEMA 4X sealing, a temperature range from -40 to +55 Celsius, that's -40 to +130 Fahrenheit, and the only moving parts are the calibration motors, which are activated for a few seconds each day while the instrument performs its automatic zero and upscale checks. The transceiver and retroreflector are the heart of any opacity monitor, as they are the components that actually make the measurement. The 4500 Mark III transceiver includes all of the intelligence, including the microprocessor, user interface, and calibration constants, as well as the main optical components. Opacity monitor accessories include an air purge system to protect the sensitive optical components from the hot corrosive stack gases, fail-safe shutters which prevent damage to the optics if the air purge fails, and also allow the user to isolate the instrument from the stack. This is especially important on positive pressure stacks, where the operator can be exposed to flue gases when the instrument case is open for maintenance or calibration. The AFU APS-IO is an interface box which includes a mains power supply, drivers for the shutters and other accessories, as well as additional inputs, outputs, and screw terminal connections for user terminations. Finally, the external zero device is used to simulate a clear stack condition for calibration and testing. For applications subject to US EPA rules, it is required for the quarterly calibration audit. The 4500 Mark III is the instrument to choose for opacity measurements. With Land's long experience, patented technologies, and excellent support, including a full 3-year warranty on the transmissometer, it represents an excellent combination of accuracy, usability, and serviceability. The 4650 PM dust monitor uses a laser forward scattering measurement. The laser and electronics are mounted on a probe, part of which penetrates the stack. Near the end of the probe, the laser shines into an interaction region where the light is scattered by any particles which may be present. The scattered light is then collected and measured. It can be used as a continuous emissions monitoring system, or PM-CEMS, when calibrated via a full correlation test. For some US EPA rules, it can be used as a continuous parametric measurement system, or PM-CEMS, which requires a much simpler initial setup without a full correlation test. The forward scattering configuration has several advantages over other light scattering techniques. The signal level is much higher, there's less sensitivity to particle size, and locating the measurement region further into the stack means it's easier to achieve a representative sampling location. These advantages outweigh the drawbacks in most applications. The main disadvantages are that the probe needs to be removed from the stack for an audit. That does add a little time to the procedure, but since audits are generally done every 3 months, it's not unduly bothersome. Here's a more detailed view of the interaction region of the LAND 4650 PM. You can see the laser beam passing through the interaction region and then passing through a hole in the collection mirror before entering the beam dump. The mirror collects the scattered light and focuses it onto a light pipe which carries it back to an optical detector mounted outside the stack. The light pipe allows us to keep all of the electronics, including the detector, in the cooler area outside the stack, so the only things in the hot environment are passive optical components. The 4650 PM offers excellent stability and reliability, with no continuously moving parts and an inherently stable optical design with several patented features. We can offer full support from our service centres in the UK, US and India. It's suitable for hot stacks with temperatures up to 250 degrees Celsius, and there's an option for going to 500 Celsius if necessary. And it offers a range of output interfaces, including 4 to 20 milliamps, as well as Modbus and Ethernet. To sum up, an accurate knowledge of your process is essential for any power plant, and AMETEK Land offers a range of high-quality products to help detect spontaneous combustion in fuel handling, and to measure dust and fine particles in stack emissions. That's all I have for today. If you have any questions, I'll be delighted to answer them now.
Okay, thank you, Derek. We are going to move into the Q&A now. Okay, Derek, our first question here is, you told us that the oxidizing fuel generates carbon monoxide, which is toxic. Is it possible that the carbon monoxide in a silo could reach an explosive concentration?
Thanks, Kim. That's a good question. It is in theory possible that you would get a toxic concentration of CO, but it's rather unlikely. An explosive concentration. The lower explosive limit for carbon monoxide in air is around 12%, and that is a lot of CO to build up. Typically, a concentration of 0.1% or 1,000 ppm would be fatal. So it's much more likely that you get a toxic concentration than that you would get an explosive concentration building up.
Okay, thanks for that. Moving on to some more questions coming in here. You briefly mentioned a continuous parametric measuring system. Please explain in more detail.
Yeah, that's taken care of with a US EPA rule. In general, PM-CEMS has to be calibrated by correlating its output to the actual dust concentration measured by a reference method. And that's true regardless of whether it's an opacity monitor or a scattered light device of some sort. These correlation tests have to follow some quite complicated protocols and involve extensive testing by a skilled test team, which makes the correlation test quite expensive. Some of the US EPA rules, for example the Cement Act, allow a site operator to avoid the full correlation test by setting an operating limit based on a parameter related to the instrument performance, for example, the scattered light intensity. In general, that operating limit will be somewhat lower than the emission limit value, typically something like 25% lower. So provided the scattered light parameter remains below the parametric limit, the site is considered to be operating within the environmental regulations. So essentially, by using a PM-CEMS, the site operator is trading a somewhat lower operating emission limit for a greatly simplified compliance test and correlation test. So you're saving money on the testing, provided your emissions are well within the allowed limits.
Okay, thanks again. Moving on to the next question here. Is air purge really needed if an opacity monitor is operating on a negative pressure process?
Yeah, that's a question I get quite often from our customers, and it is tempting to save money by omitting the air purge system and just rely on the draft within the stack to draw ambient air through the purge system and keep the optics clean. I've seen it done a few times, and it sort of works. My concern is always that there's going to be some contamination, so you're going to wind up having to do more frequent maintenance, clean your optics, and so on. And the bigger danger is that there will be some fluctuations of pressure within the stack, and that these will actually expose the sensitive optical components to hot and corrosive stack gases. And when that happens, you get damage occurring really quite quickly. So in general, I would not recommend doing without air purge, and absolutely definitely not for any optical components that are being used for compliance purposes where your site operating permit absolutely requires these things to be operating correctly.
Okay, another question for you here. What is the typical range of cost for a PM-CEMS, including both the initial capital and installation costs?
Yeah, it can vary quite a lot. It depends on the manufacturer. It depends on the options selected. It depends on whether you're calibrating it as a PM-CEMS or PM-CEMS. An opacity monitor, for example, doesn't need the correlation test if you're reporting opacity as a percentage. But typically, as a starting point, if people are drawing up a budget, you probably want to start with a budget of around $25,000 US. You can shape a few options off that if you want to reduce the cost, and you can add some additional options to really get a fully featured system that has every option you could want. But that's a fairly reasonable starting point.
Okay, another question here. How do I choose between an opacity monitor and PM-CEMS?
In most cases, that's actually a choice that's already been made for you by the environmental regulations. If you're required to report opacity in percentage terms, then you require an opacity monitor, a transmissometer. If you're required to operate or to report your emissions in milligrams per cubic meter of dust, then you're looking at a PM-CEMS. There are some overlaps. An opacity monitor can certainly be calibrated to measure in milligrams per cubic meter, so you can actually get both measurements out of the same device. And some US EPA rules, for example, the mercury and air toxics, the MATS rule, have provision for either a PM-CEMS or an opacity monitor, and you've simply got different quality assurance rules to take care of depending on which way you go with that. In most cases, it's better to choose an opacity monitor if you have the choice, because it avoids the entire need for a correlation test, and that's a significant saving both in the initial setup and calibration and in the ongoing quality assurance and quality control. Quality assurance for an opacity monitor is much, much easier than it is for a PM-CEMS.
Okay, thanks again. Another question for you. You said that infrared temperature sensors can only measure the surface temperature of the fuel. Is there any way to measure the temperature of coal within a storage pile?
That would be really nice if it was possible. Unfortunately, I don't know of any non-contact measurement that can look inside a coal pile. An X-ray thermometer would be wonderful if one existed, but I've never come across a practical technology for that. So really, the only way to make a measurement of the temperature within the stored fuel is to use a physical probe, such as a thermocouple, and push that into the coal pile.
Okay, just a few more here. Where is the best place to install a CO sample probe in a silo?
Right, we're measuring the CO concentration in the headspace of the silo. So that's in the gases and the airspace above the stored fuel. Therefore, the probe has to go into the silo above the highest possible fill level. It has to be out of the line of fire, basically, out of the line where the fuel is falling into the silo as the silo is being loaded. what I've seen quite often are access ports in the top of the silo off to the side, and those are ideal. So you can fit the probe into those ports and then ensure the probe penetrates far enough into that headspace to ensure that it's getting a representative sample of the gases in the silo. One thing that's also worth noting, you do need to be measuring a representative sample of that headspace. But the good news is there's usually enough natural convection within a silo to ensure that the gases in the headspace are well mixed. So in general, a single sample point will get you a representative sample of everything that's going on in the silo.
Okay, another question here. How do I choose a suitable alarm level for my safety system?
That is really quite a practical question because there's no simple answer to it. Whether you're looking at a temperature monitor or a CO monitor, you need to find an alarm level that will unambiguously identify a problem, but which is high enough that it will not give you nuisance alarms and indicate that there's a problem when really it's just a normal process fluctuation. In my experience with CO monitors across a number of sites, a number of users, a good starting point for a CO alarm is somewhere between 100 and 200 parts per million. That's well above any level where the instrument drift is going to give you a nuisance alarm. In most, but not all cases, that's high enough that it will not give you a nuisance alarm because of normal process fluctuations, but there are exceptions to that. But it's certainly low enough that you will still get a rapid indication and a rapid alarm taking place when the process does begin to get into a bad state and where you do begin to see spontaneous combustion going on. For temperature monitoring, it really depends on whether the fuel is exposed to solar heating, because that's one of the biggest influences. Bright sunlight will warm the surface of the stored fuel, particularly coal is black, so it absorbs sunlight quite readily. So the alarm threshold for temperature monitoring has to be somewhere above the maximum temperature that you're going to get caused simply by solar heating of the fuel. So I've seen people start with alarms in the 120 to 130 degrees Fahrenheit region. I think that's somewhere in the 50 Celsius or thereabouts for people using Celsius. But again, it's a practical question of where do you get good sensitivity without getting nuisance alarms taking place.
Okay, well, we're going to be wrapping up the webinar right there. Thank you to our presenter and for spending some time with us today. And thank you to all of our audience members for being a part of this webinar event. Take care, and we'll talk with you soon.